So looking back, we got involved in system architectures and rack architectures. That led to modularity and the NIC module development. We recently launched the NIC 3.0 module last year, and we actually have samples and working systems to give you an idea of the performance that's now available on this very small daughter card and the modularity up in the experience lab. That led to, again, this year, more modularity, more system design. And if you look at this is, lots of neat things here. But there's also an opportunity to shift left and get involved at, I'll say at the silicon level. And so last year, in March, we announced the creation of a chipset architecture project. It was called and is called the Open Domain Accelerator, ODS, Open Domain Specific Accelerator, project. And it defines an architecture on how chiplets that are put together and together perform an accelerator function to address some of those needs that Misha talked about earlier. So, why do you put chiplets together? Well, we know that there's an opportunity when you have a very specific accelerator that handles and designed to handle a specific workload, that there's a tremendous performance opportunity. The graphs below show, as an example, the combination of a Tensor processor unit and a CPU can produce 34 times more performance than just a CPU. The one on the right is a network application, and again, the combination of a network function processor along with a CPU host gives you, again, that scalability of 5 or 6 times performance advantage over traditional software implementation. So this is the type of breakthrough that we're looking for. Obviously, there's some performance per watt efficiencies that we're also trying to achieve. So that's why we're interested in these very specific accelerators. The idea is you want to put together these devices, these application-specific devices, and make the best choices to build up a device. And we want to do that because it's cost-effective to do that. There's white papers and information that's being shared across the team that it's actually up to 30% less expensive to have multiple die on a single SoC versus having one very large monolithic die and the manufacturing cost associated with that large monolithic die. There's also an opportunity to take different die from different suppliers that's very good at a specific function. Maybe it's an FPGA function, maybe it's a special network processor function, or a service processor function. It may have another processor, another die that handles memory management, yet another one that could handle I/O functions. And by taking the best-in-class die and putting those together, we get potentially breakthrough performance if we can put all of that onto a single SoC. The other advantage is that we can mix and match the best process technologies for those different devices, and again, achieving some breakthrough performance. So that group has actually spawned 3 different work streams. The first was to define the interface and standards in which we can interconnect these various dies from different companies. When you start to interconnect die from different companies, there's some business challenges that we have to address. The easiest one to describe is just test. We're now testing at a die level, not necessarily at a device or package level. So the test vectors are going to be different at the die level. We have to assure we have good die before we package it, and then we got to retest it again at the package level and coordinate the testing, which tends to have a lot of individual IP in it and exposure of IP. We need to resolve that so we can test the whole package and deliver a fully functional, tested, and validated product. So that we're looking at business practices. We also have to define the interconnect, and the direction that the team has headed is to approach this as what they call a bundle of wires or a bunch of wires. and interconnect these through a wiring scheme. On paper, it sounds really good, but really, is that going to work? And so they launched, a few months ago, launched a project to actually build a proof of concept. And I get the opportunity to actually show you that work effort. This thing just came out just a few days ago, and there's limited prototypes, but maybe you can zoom in on this. This is the prototype for a bunch of wire interconnect. Now, obviously, this is a huge card, but think about what we're really trying to demonstrate is that there's in each one of these blocks is an individual die. There's a network, in this particular one, there's a network processor, there's an I/O function, and an accelerator function. So we're demonstrating that we can actually connect these together through this interconnect scheme that's being defined, and then allow that to have an interface, a standard interface to PCI. This will become the development vehicle. And again, started just a few months ago with an idea. Tremendous number of companies that have gotten involved in and interested in this. We went from a workshop of a few dozen people to a workshop here a couple of weeks ago at IBM research facility in Alameda. We had about 140 engineers that spent the day talking about how do we do this. We actually now have over 20 companies that are involved in this project. In fact, I heard last night it could actually grow to 25 companies. A lot of big names. In fact, recently Microsoft got on board and wants to get involved in this. We have other companies. IBM is involved. Intel's involved. Xilinx and others. So it's very exciting that we have that level of support. We also reached out to IHS Markit a few months ago, and IHS Markit has been working with our organization now for 3 years. And we asked them to help quantify how big is this opportunity. And last night we got some email on their initial findings. They've been doing some interviews with people and trying to quantify the market size. They came back and told us that this opportunity, the share of available market for this SoC design, is expected to hit $50 billion in the next 15 years. So by 2035, this could be a $50 billion market. So it's pretty exciting that we're actually on the front end leading that. So real quick, they've defined a method to exchange data, and you got to have that in place so you can do your simulations. They introduced and released a white paper today that described this bundle of wires proof of concept that you see over here on the table, and very excited that they achieved that milestone of that they set out in just a few months. And again, tremendous effort from all the companies pitching in engineering resources, throwing money at it to help build the prototypes, and really rolling up their sleeves to get to this point. So it's very exciting. I know that they're looking for some software engineers now that they got the hardware. So if you're a software person, go talk to that group. And again, they'll have some more data or some other disclosures later on today so you can understand more about that. So anyway, enough about projects. I'll take a break. It's really great that I get to introduce the next person, our next speaker. She's a guest speaker, for our keynote today. She's been involved in dozens of startups. She got involved in the storage industry and saw the amount of waste that is produced by the storage industry. She's been involved in the textile industry and witnessed the amount of waste in the textile industry. It's really become her passion to change the behavior of all of us so that we don't think of things as a linear consumption model, but rather a circular consumption model, where we take what we don't need today and we, provide it to other people so that there is a secondary user market. And they've done some really interesting work to show the value of that. So With that said, I'd like to introduce Ali Fenn, Chief Innovation Officer for IT Renew.